We will start with today's session. Today we have Algebra of Limits. How limits will work. We have already studied the definition of limits. We have also studied the existence of limits. Today, if I know that two limits will exist, then what can I say about the sum of those functions? If I have two functions, the sum of the functions, what happens to the limit? The difference between the functions, what happens to their limit? If I take the product of two functions, what happens to the limit? If I take the division of two functions, if I take the ratio of two functions, what happens to the limit? So this is a theorem we have for today. Let f of x and g of x be two functions such that limit x tending to a f of x is equal to L and limit x tending to a g of x is equal to m. Then the following are true. Limit x tending to a f of x plus g of x becomes L plus m. Limit x tending to a f of x minus g of x becomes L minus m. Limit x tending to a f of x into g of x is L into m, and limit x tending to a f of x by g of x is L by m, provided m is not equal to 0. We'll analyze what the theorem says. If I am given two functions f of x and g of x, and I know that as x goes to a, the limit of f of x is L and the limit of g of x is m. Then what happens to the function f of x plus g of x as x goes to a? That is the thing, but the sum of the limit of the first function and the limit of the second function. Similarly, if I take the difference between the functions f of x minus g of x, then when I take the limit x tends to a, it becomes the difference of the limits. Similarly, the product, if I take f of x into g of x, the limit becomes the product of the limit. If I take the ratio of two functions, the limit becomes the ratio of the two limits, provided I don't have a division by 0. We'll now go to the proof of this theorem. In the proof, we will use the definition of limits, which we have told previously. I have, for the first one, we are given that limit x tends to a, f of x is equal to L, and limit x tends to a, g of x is equal to m. I will take the first given limit x tending to a, f of x is equal to L. By definition, it says that given epsilon greater than 0, there exists a real number delta 1 greater than 0 such that whenever modulus of x minus a is greater than 0 and less than delta 1, we have modulus of f of x minus L is less than epsilon. Also, we are given that limit x tending to a, g of x is equal to m. This implies whatever epsilon is given, I can find a real number delta. I will take the same epsilon. For the same epsilon greater than 0, there exists a real number delta 2 greater than 0. Because two limits are there, I will take two numbers. One I will call delta 1 and another one I will call delta 2, such that whenever modulus of x and a, distance between x and a is greater than 0 and less than delta 2, modulus of g of x minus m will be less than epsilon. I have to prove the first part. I have to prove by definition. So what I have to prove is, given any epsilon greater than 0, I have to find a delta such that whenever modulus of x minus a is less than delta, the distance between the function and the limit should be less than epsilon. So what I'm supposed to do is, I'm already given a epsilon greater than 0. I have to find a delta such that for modulus of x minus a less than delta, the difference between the function, now the function is f of x plus g of x and the limit is L plus m. Distance between f of x plus g of x and L plus m should be less than epsilon. First I will fix a delta such that both these two conditions are satisfied. We have done this in the uniqueness of limit theorem. The first condition is satisfied when modulus of x minus a is less than delta 1. Second condition is satisfied when modulus of x minus a is less than delta 2. By what we have done in uniqueness of limit, I will choose a common value of delta. Let delta is equal to minimum of delta 1 and delta 2. Now when delta becomes minimum of delta 1 and delta 2, both these conditions will be satisfied. Therefore, whenever modulus of x minus a is greater than 0 and less than delta, we have both modulus of f of x minus L is less than epsilon and modulus of g of x minus m is less than epsilon. Now I need this quantity, modulus of f of x plus g of x, the distance between the function and the limit. Limit I am supposed to prove that it is L plus m. What I will do now is, I will put f of x and L together and g of x minus m together. By our triangle inequality, modulus of a plus b is less than or equal to modulus of a plus modulus of b. Therefore, this I will consider as a, this I will consider as b. This is less than or equal to modulus of a plus modulus of b. Okay. Now, by the above condition, whenever modulus of x minus a is less than delta and greater than 0, modulus of f of x minus L is less than epsilon and modulus of g of x minus m, this also is less than epsilon. The sum of those two will be less than sum of epsilon plus epsilon. Okay, so this is less than 2 epsilon. So what we have done now? I have a epsilon greater than 0. We had taken an epsilon greater than 0. I have found out a new delta. New delta is minimum of delta 1 and delta 2 such that whenever modulus of x minus a is less than delta, the distance between the function and the limit is less than 2 epsilon. Therefore, by definition, limit x tending to a f of x plus g of x is equal to L plus m. This is the function and this is the limit. Therefore, this is the proof of the first part. Similarly, instead of taking f of x plus g of x, here if I take f of x minus g of x, I can prove the second part. Let's go to the third part now. Now I have to consider the product of the functions. What happens to the limit when I take the product of the functions? Whatever it is, I will take an epsilon. Here I will choose a special epsilon. What I will do is, I will take an epsilon. Let epsilon 1, I will call it, be greater than 0 and less than 1. I can prove the definition for any value of epsilon, but particularly here I will take an epsilon greater than 0 with the condition it is less than 1. I will call that as epsilon 1. Now I am given that limit x tending to a f of x is equal to L I will apply the definition for the same epsilon I have taken here. So given epsilon 1 greater than 0, there exists delta 1 greater than 0 such that modulus of f of x minus L is less than epsilon 1 whenever modulus of x minus a is greater than 0 and less than delta 1. This condition can be written before this and this can be written afterwards also. Similarly, I know limit x tending to a, g of x is equal to m. Therefore, given the same epsilon 1 that is, there exists a delta 2 greater than 0 such that modulus of g of x minus m is less than epsilon 1 whenever modulus of x minus a is greater than 0 and less than delta 2. We'll keep this now. Now again I want a delta which satisfies both these conditions. I will choose as before, let delta is equal to minimum of delta 1 and delta 2, so that when modulus of x minus a is less than delta, that means both the conditions are satisfied, these both conditions will be satisfied. Therefore, whenever modulus of x minus a is greater than 0 and less than delta, modulus of f of x minus L is less than epsilon 1 and modulus of g of x minus m is also less than epsilon 1. Now, one more thing we'll do in this case, I will see what happens to modulus of g of x. Modulus of g of x, with g of x I will add and subtract m, g of x minus m and plus m. Again by triangle inequality, modulus of a plus b, this is less than or equal to modulus of e plus modulus of b. And modulus of g of x minus m, this is less than epsilon 1 when modulus of x minus a is less than delta. So this is less than epsilon 1 whenever modulus of x minus a is greater than 0 and less than delta. This will remain as plus modulus of m. This epsilon 1 I have taken to be less than 1. Therefore, this epsilon 1 is less than 1 plus mod m. Therefore, I get modulus of g of x is less than 1 plus mod m. This simply means that this is bounded. This is less than or equal to a particular number 1 plus mod m for every value of x. Therefore, this is bounded. Keeping this, now I have to apply the definition for f of x into g of x. For a particular epsilon, I have to find a delta such that modulus of the function is f of x into g of x, modulus of the function minus the limit is L into m, I should get it as less than epsilon whenever mod x minus a is less than delta. So I have to show that this will be less than epsilon whenever mod x minus a is less than delta. We'll keep this. I will try to alter this. I will add and subtract L into g of x. We'll see why this is necessary. L into g of x minus L into m. I will combine the first two terms and the second two terms. So this becomes first two terms g of x is common into f of x minus L. Second two terms L is common into g of x minus m. Now this is of the form mod a plus b. This is less than or equal to modulus of a plus modulus of b. Mod a into b is equal to mod A into mod B. So this can be written as equal to modulus of A into modulus of B plus modulus of A into modulus of B. First term I have taken as L, second term is this. First term is g of x, this is the second term. Now modulus of g of x is less than 1 plus modulus of m when modulus of x minus a is less than delta. When the same condition is holding, modulus of f of x minus L, this also will be less than epsilon 1 plus mod L. Again with this, under this condition, modulus of g of x minus n is less than epsilon 1. So under one condition here, all these conditions are satisfied. Okay. Now I'll take epsilon 1 common here. Epsilon 1 into 1 plus mod m plus modulus of n. This is equal to, from this step to this step, this is less than. Okay. Choose epsilon equal to 1 by 1 plus mod m plus mod L into epsilon 1 as equal to epsilon by this one. Okay. Now what will happen to this? I will substitute here modulus of f of x into g of x minus ln. Here it is equal to, then it became less than or equal to, then again equal to, then less than, then equal to. So the highest inequality I have is less than, so this is completely less than. I will substitute for epsilon 1, it is epsilon by 1 plus mod m plus modulus of L into 1 plus mod m plus modulus of L. I am substituting for epsilon 1 here. This is true whenever 0 less than mod of x minus a, that is less than delta. Now these two will cancel. Therefore, modulus of f of x into g of x minus L into m is less than epsilon whenever 0 less than mod x minus a is less than delta. So, given any epsilon, I have found a delta such that modulus of f of x into g of x minus Lm is less than epsilon. Therefore, by definition, limit x tending to a f of x into g of x is equal to L into m. This completes the proof of the third part. Fourth part can be proved similarly.